Hi everyone, welcome to another video for Knees 7103. This is the third in our series on chapter 13 about ill-mannered error terms. In this video we're going to be talking about outliers, and specifically outliers among our residuals, which allow us to detect unusual values in Y. So when we're identifying residual outliers, we want to refresh ourselves of exactly what a residual is, right? And the residual is the difference between the actual data and our model's predictions, right? So it is an error that results from the difference between the real data and what our model predicted. So when we calculate residuals in this way, we would get what we would call a raw residual, right? It is just the straight difference between the actual data and what our model predicted. And if we had a positive value, that means the actual data was greater than what our model predicted. If we had a negative value here, then that means the actual data was less than what our model predicted. So if we look at residuals in that sense, there are going to be a few problems if we just use raw residuals as a measure of error. The first is the scale, because unless we standardize these residuals in some way, if we just plot the raw residuals, that means that larger scales are always going to look like they're more errorful than smaller scales. So for instance, let's consider if we have models that predict people's race time in seconds for the mile versus the 100 meters. Right? The 100 meters might be over in 10 seconds, whereas the mile is going to be over in, somewhere between 4 minutes to 6 minutes, right? Depending on what level of racer we're looking at. So the actual deviations away from our model predictions in the 100 meters are going to be tiny fractions, right? They might be decimals of seconds. Whereas the deviation away from our model predictions for the mile might be in hundreds of seconds, right? Even depending on how good our model is. So if we have raw residuals and we don't scale them in some way, the larger the scale is, that means the more room there could potentially be between the actual data and our model estimate. And therefore, it will look like we have bigger errors, when in reality, that's a property of the scale, not a property of our error. Right? So we need to scale these terms in some way. The other consideration we have to take into account is exclusion, because if we have extreme values in our data to begin with, it's going to inflate any measures of variability. Therefore, if we try to scale these residuals, for instance, dividing them by maybe the standard deviation of our residuals, that's going to include one really large value to start with. And that's going to pull that standard deviation up, right? And it's going to make that variability larger than it otherwise would be had that value been excluded. So paradoxically, this will make that value appear less extreme, because any data set that contains that extreme value, if we calculate a variability statistic, right, some measure of spread, that measure of spread is going to be widened by the extreme value that's contained within it. So we oftentimes will want to exclude that value, calculate our measure of spread on the remaining data, and then normalize to that value in some way. So we can see that if we again refer to our example from the book where we were looking at SAT verbal scores and high school graduation rates. And we said we have this one example where the two columns, the entries for this person were flipped. So the 86 that should have been their high school graduation rank was actually put over here into the SAT verbal column. And so if we plot these data, right, we have this extreme value on the y-axis. And this person has a much larger SAT score than anyone else's, because obviously these things are on different scales and this number didn't really belong over here. We can see that pretty clearly if we actually plot the distribution of the y-axis. So if we look at just the y-axis, ignoring x for a moment, this is how those SAT scores are distributed. Now, you can see that we have one very clear outlier here, where it is a massively more positive number than any of the other values that we have on the y-axis. If we just look at the residuals, which is to say the differences along this regression line, though, what we're going to end up with is a relatively symmetric distribution of residuals, right? So although this one positive value tended to be a quite positive residual, it's balanced out by other quite negative residuals. But the misleading thing here is, of course, is that this best fit line is fit to something that includes that data point. So the inclusion of that data point is pulling the best fit line up towards it. And had we not had that value in there to begin with, that data point would have looked like a much bigger residual, right? So this is, again, thinking about that issue of inclusion. Because these residuals are calculated based on a best fit line that includes that data point, that means this large outlier actually looks like less of an outlier because it's already pulling the best fit line in its direction. So in order to address this, the book recommends using something called studentized residuals. And some programs will give you studentized residuals. Other programs will give you standardized residuals. But in general, they all favor the idea of giving you deleted residuals, where you're trying to take a calculation where you exclude the influential data point in some way in the calculation that you are taking. So by default, R uses standardized residuals. So I'm going to talk a little bit about what those are. They're different from what you would get if you calculated the studentized residuals, but if you refer to the R script for this module, you'll see both methods of calculation. By default, you'll get the standardized ones, but you can use the R studentized function in order to extract the studentized residuals from any sort of linear model that you have. So again, the formula for these standardized residuals isn't terribly important compared to understanding conceptually what it means, right? But here is the formula for calculating our standardized residuals, where our error term, and in this case I'm indicating that it's standardized and there's some deletion that's taking place. And we're looking at yi, right? So our individual data point minus the predicted value. So that gives us our raw residual or our error term. And we divide that by the standard deviation or the mean squared error of all the residuals. So all of the remaining variance in the model. But we update that for each calculation by making an adjustment based on its leverage. So for each unique data point that we're going to have, right, and what our model predicts, if it was a large lever, we're actually going to weight that proportionally down here. So we're doing 1 minus that leverage term, and then we're taking the square root of that, multiplying that by the standard deviation. So the larger h is, right, this is going to get closer to 0. So then we're multiplying the s term by a smaller fraction, right? So we are going to get then something that makes this smaller the closer h gets to 1. So what that's going to do is ultimately provide a unique weight to each of the residuals we're trying to calculate, and it's going to penalize more influential variables to a greater degree, so that this will then exaggerate their error. So it's not quite the same as calculating it as if it wasn't in the data to begin with, but we are taking some amount of the leverage into account in the calculation of these standardized residuals. So when we do this, we can use the plot function in R, and we can say plot, and then we can give it the name of a general linear model, as we do in the script that accompanies this module. And here's our first plot, which is just the actual data that we had, right? So this is the SAT scores as a function of those high school ranks. But then once we plot the linear model, R will prompt us to press enter to see the next plot. And if you press enter, you'll go through a series of plots, one of which is this residuals versus fitted values plot. And you can see this kind of V shape that we get here. And on the y-axis, we're looking at the residuals. Notice that these are the raw residuals, so these are signed values. And on the x-axis, we're showing this as a function of the fitted values, which is what our model predicts. So these are the predicted SAT scores on the x-axis, and this is how far off we were on the y-axis. The issue, of course, right, is that we said if we just do these raw residuals, this extreme outlying data point, right, which was point number 6, which is the same as over here in this top corner, is already being included in the calculation of the regression slope. So it's already pulling our model towards it in the calculation of these residuals. If we look at this instead on what's known as the scale location plot, which is one of the other plots that R will give you by default, what you get is the square root of the absolute value of the standardized residuals on the y-axis, right? So the square root transformation reduces everything, right? The absolute value obviously transforms everything into an absolute value, and then those standardized residuals, right, takes that leverage into account for each of these unique data points. And you can see that when we looked at the raw residuals, data point number 13 and data point number 6 were about the same in terms of how far off the line they were. Because if this is our data point number 6, you can see how far off the line it is here. This is data point number 13. You can see how far off the line it is here. So those are similarly sized raw residuals. When we take that leverage into account and calculate the standardized residual, now you can see that number 6 is actually much larger than number 13, right? And so data point number 6 is actually much more of a concern because it has a much larger variance relative to any of the other data points that we're fitting, right? So this error term is much larger relative to any of the other error terms that we're observing for the data points in this model. Now, for the calculation of studentized residuals, it's really done in a very similar way, right? And in the code for this, I actually show you how to use the rStudent function to get a studentized residuals out of the linear model. But it's going to show us a very similar pattern. Now, visually, it looks like this. So on the left-hand side here, highlighted in black, we have our standardized residuals as a function of the fitted values. You can see, again, most of our data points fall around 1, or somewhere between 0.5 and 1, right? But that 6th data point, where we had that transposition of the two numbers, it has a very high standardized residual. Now, if we actually do this as the square root of the absolute value of the studentized residuals, which again means that we are completely removing that error term before we do the calculation, what we're going to get is a much larger variation. So the standardized residual makes that point stand out. The studentized residual makes that anomalous point stand out even more. And again, the reason for this, if we look at their formulas in these terms, is because the calculation of the standard deviation here is the calculation across all residuals. So it includes all the residuals in there, even the one outlying residual. Whereas here, we actually calculate a unique standard deviation at each point, which is the standard deviation of all the residuals except the current one. So that we do this as a calculation omitting the current data point, which then makes this one look a lot farther away, because when this data point is excluded, the variance among the residuals is a lot smaller, which makes the resulting studentized residual that much bigger, right? Because if we have a smaller term in a denominator, then that's going to make the ultimate term a lot larger. So this data point, or sorry, this outlying residual stands out as an even larger outlier when we use the studentized residual.